Welcome to our final lecture for Physics 152. Final lecture, Union College, I suppose. We are going to now just review the last sections of the semester. So chapter 28 was relativity. So make sure you understand the postulates of relativity. And of course, you can just go back to the review that I did a few days ago for exam 4 for more detail about these things. But just reminding you, we have postulates of relativity, which is the speed of light in vacuum is a constant in all inertial reference frames, and the laws of physics apply in all inertial reference frames the same. Understand why we have to have time dilation and length contraction. It's not possible to have something going close to the speed of light and not have these occur. It's very important to be able to identify what reference frame has proper time and proper length. They're not the same typically. And then understand how to apply time dilation and length contraction equations once you've identified which reference frame has the proper time and proper length. Remember that Lorentz constant or factor, not a constant, and our time dilation equation, the dilated time is gamma times the proper time. Our length contraction equation, the contracted length is the proper length divided by gamma. Then you should be able to apply relativistic addition of velocities, and we're only doing parallel velocities. And be able to work with relativistic momentum. P is equal to gamma mv. And energy. Particle nature of light. Up through chapter 28, we had learned about the wave nature of light. We learned about Thomas Young getting his Nobel Prize for showing the light had to behave as a wave. And so we have a couple different things here that light has to be a wave to do these things. And polarization has to be a transverse wave. But now we have particle effect things that say light has to be a particle. So we have Einstein's photoelectric effect. We had the Compton scattering that could only be explained with a particle nature, the X-rays with their characteristic peaks, and pair production. All of these require that light comes in packets of energy that we call the photon, with the energy for a photon equal to hf, where h is Planck's constant. So based on this, we have a duality, a wave-particle duality, where we say that light is both a wave and a particle, and depending on what you're looking at, you use one or the other to describe it. And then we have de Broglie, who said if light can do it, so should other things. So something like an electron has a wavelength of Planck's constant divided by its momentum. And experiments prove this out, that light indeed is a wave or particle, and electrons are indeed either a wave or a particle. So quantum mechanics is treating the wave nature of a particle. So primarily we use quantum mechanics on very small things because that's the only time when we see a difference with quantum mechanic calculations. The quantum mechanics has to give us correct predictions in classical physics, but it's just a lot harder to get there. Make sure you understand the different models, the Plum pudding model of an atom, the planetary model, the Bohr model, and the quantum model. You should understand why each one was developed, what its strengths were, what its weaknesses were, and why ultimately they were all abandoned until we got to the quantum model, which is the current one. We have 4 quantum numbers: the principal quantum number, the orbital quantum number, the orbital magnetic quantum number, and the spin magnetic quantum number. Those 4 quantum numbers describe the energy state, or maybe I should just say the state, of an electron orbiting a nucleus. The Pauli exclusion principle applies to all fermions. And we are usually only worried about electrons, but protons and neutrons are also fermions. They also have the Pauli exclusion principle. And it says that for any indistinguishable fermions, such as multiple electrons in the same atom, They cannot have the exact same set of quantum numbers. At least one of them has to be different, or it cannot have a wave function. It can't exist. Hund's rule is simply saying that electrons are going to go to the lowest energy possible. And if the magnetic moments are aligned in the same direction, that's a lower energy than if they're aligned opposed to each other. So they will try to fill going the same direction as much as possible. Chapter 31 was radioactivity and nuclear physics. So this is where we learned about radioactive decay. So you need to be able to describe what's going on with alpha, beta, gamma decays. Make sure that you can relate half-life to decay constant, understand why we have an exponential decay, calculate the disintegration energy and binding energies. And now newer stuff. Chapter 32, medical applications of nuclear physics. I know a lot of you are taking this class for medical professions. So this is something that hopefully was more interesting to you. I identify why we use radioactive dyes that give off a radioactive emission in the body. The answer is because then we can see where the dye is flowing. So if you put the dye in the blood, you can see where the blood goes. You can see if it's leaking out, things like that. Explain how an Anger, named after Hal Anger, camera works. That's a gamma camera. Remember, it has lead that makes channels. So you have a source over here that's giving off gamma rays in all directions, and only gamma rays that go straight through a channel can make it through. So it allows you to see where they're coming from, even though you're throwing away almost all of your gamma. Be able to differentiate and calculate radioactive dose. Remember, a dose is the energy absorbed per mass, and the absorbed dose, which is the energy absorbed per mass, times the RBE. And that's telling you about how much damage potential it does. So the absorbed dose is the one that's really the important one. That tells you what the potential is for damages. Make sure you know what the damage is that ionizing particles can do. You know, what happens when your body absorbs ionizing radiation, and why it causes cancer, but also why we use it to treat cancer. And finally, describe how proton treatment is superior to electron treatment. Remember, proton treatment, it deposits most of its energy in a small region, whereas the electron treatment, it would be something like this. So it has a lot more energy as a proportion to the total that's deposited on the way in, meaning that you're damaging a lot more tissue besides the one that you're trying to target. I suppose I should say, radiation, if radiation is ionizing, it can break bonds in your DNA. And then those bonds, if they reform incorrectly, they might just go into permanent hibernation. Well, that's no big deal. They might go through programmed cell death, apoptosis, which isn't a big deal unless you have a huge number of them doing this. And actually that applies for the first one too. If you have a large number of cells that are doing apoptosis, then you have radiation sickness where your body can't keep up with the number of cells dying. That's bad. Or it can form incorrectly and then rapidly reproduce, and that's a cancer, and that's bad. So that's how it creates cancer. So why do we use it to treat cancer? Because we can deposit a huge amount of area of energy in a relatively small area, and that energy can then cause, sure, it'll cause some mutations, but it'll cause a whole lot more cell death. And so if you can kill all the cells in that tumor, well, you've killed the cancer. We also had in this chapter nuclear fission and fusion. Now, I am a big believer in nuclear power. Nuclear fission is the kind of nuclear power plants that we have right now. And so I talked about the nuclear power plants and what they need. You have fuel rods, usually something like uranium-235. You could also have plutonium. I think it's Pu. 239. Either of those will work as a fuel for the fuel rod. And then you have some breeder reactors that are uranium-235 plus uranium-238. And the uranium-238 is built up through the reaction to produce plutonium-239 that then continues it. So those are breeder reactors, are converting uranium into plutonium that will then be fuel. So you have the fuel rods. They're in rods so you can easily take them out, replace them, etc. Moderator, typically water, like heavy water. May not have started heavy, but it ends up heavy. Heavy water means that you have deuterated and tritiurated, deuterium and tritium for hydrogen. And that causes neutrons that come off after a fission event to slow down so that they can cause another fission event when they get to another rod. Control rods, often made out of something like cadmium, they absorb neutrons. And so these can be lowered or raised so you can control the reaction. You want the reaction to be critical, which means for every fission event, one more fission event is going to occur. So the reaction rate stays constant, the temperature stays constant, and then you have water separate from the moderator, water that flows through a heat exchanger that takes heat out of your reaction chamber to a steam power plant where you use steam power. So that's fission. What are the upsides of fission power? Well, it produces good energy. The fuel is just uranium that's in the earth. Now that uranium is mostly 238, so they have to enrich it by separating the 238 from the 235. But you know, the fuel is something that's already in the ground, it's already radioactive, and then they use it for producing energy. It has very little pollution. Virtually no radiation escapes from a fission power plant. So what's the downside? Well, the downside is after you're done, you have radioactive products that are produced in the fission reactions, and you have to find a way of storing that radioactive material. Even though you started with naturally occurring radioactive material, once you've taken it out of the ground, you have a responsibility what you're going to do with it. And so that's a problem, is what do you do with the spent fuel rods? Another problem is, what if something goes wrong? What if you have a big bang, i.e. Chernobyl? That's bad. Nuclear fusion is something we would like to make power plants with, but right now we don't have any way of doing it because it's so hard to control the fusion reaction. Fusion reaction has a much greater amount of energy per gram of fuel that's available. Fusion, something like fusing hydrogen to helium, releases much more energy per nucleon than fission going from uranium toward iron. Fusion can occur with anything that's smaller than iron moving toward iron. Iron is the most stable nucleus, so that's why fusion ends there. Fission will release energy if you go from something bigger down toward iron. So fusion power plants, that's all the research. There's a huge amount of research that goes into trying to figure out how we can make a fusion power plant. Now, what's the difference in a bomb and a power plant? A bomb is not controlled. A power plant is controlled. So it's a lot harder to make a power plant than it is a bomb because you don't have to control the bomb. So nuclear bombs, good or bad, right? It's an ethical question. This is something that is actually one of the goals for this class, is for you to understand the ethics involved in applying science. And you know, those scientists who worked on the Manhattan Project to create the first nuclear fission bombs, they thought it was absolutely necessary to preserve freedom, which I know is kind of laughable right now when we're being told we have to stay in our houses and we can't go anywhere. But they fully believed that they were doing the ethical thing. They were trying to develop what they were sure that the Germans were working on developing. And the Germans did start on it, but they stopped their process just largely because Hitler was a racist. But they thought they were doing absolutely the right thing. But then when the bombs were used, first on Hiroshima and Nagasaki, the two fission bombs, the one was a uranium-235 fission bomb, and one was a plutonium-239 fission bomb, and they saw just the amount of destruction that they had made possible. They felt so guilty that they had created this weapon of mass destruction. And so there's a lot of ethical concerns. Did they think it through when they came in, or were they, a lot of people will condemn them, and other people like me say they thought they were doing the right thing, and afterward they realized it wasn't the right thing. Well, some scientists went on to make the fusion bomb after the fission bomb was complete. A lot of them refused to work on it. And the fusion bomb has a much bigger energy release. So when we talk about atomic bombs these days, we're usually talking about a fusion bomb. If they say a hydrogen bomb, that's a fusion bomb. And those are just much bigger payloads. Chapter 33, which is our last chapter, forces are mediated by particles, is a particle physics idea. And these particles are not real particles, they're virtual particles. They're not particles we can detect, we can only see their outcomes. So it's kind of confusing. These particles that mediate the forces are called gauge bosons. It's actually called gauge theory, is the theory of these particles that mediate forces. And so gravity has the graviton as its gauge boson. Electromagnetic has the photon as its gauge boson. The weak force has the W plus, W minus, and Z particles. And then the strong force has gluons. So each of these has its own gauge boson. Bosons means that they have spin equal 1, or 0 or minus 1, but gauge bosons all have spin equal 1. Now I said explain how beta decay works. What we had before was beta decay was something like carbon 14 produces nitrogen 14 plus a beta minus, it's just an electron, plus this antineutrino. Or if you put it in a single nucleon here instead of the carbon, that would be a neutron 0, 1 produces a proton 1, 1 plus minus 1, 0 beta. But now when we look at the particle physics, we have a neutron is an up, down, down, produces an up, up, down, plus the electron, plus the anti-electron neutrino. So what you had here was a down, well, the way I made it was the middle down, decayed into an up, and this electron, the electron neutrino. And so we had the Feynman diagram that showed, and I've got to change the order, up, down, down, up, down, up. So there's a down and up. And then you have here that produces the and let's see, this is going to be an anti-up here. And this is, yeah. So it's a down anti-up. And so that's a Feynman diagram showing how the decay worked. Things that are conserved in a particle decay. Energy. Energy is always conserved. Momentum, these stars mean partially conserved. Momentum was partially conserved if the net external force is 0, which for a particle decay is always true. Charge, always conserved. Baryon number, always conserved. Lepton number, that is the number of electrons and muons and tau particles. The electron itself, the electron number is partially conserved, the mu is partially conserved, the tau is partially conserved, but the sum of those is completely conserved. And then quark number. So baryons, what is a baryon? A baryon is something made of 3 quarks. So in essence, you could say the baryon number being conserved means the quark number is conserved. But the quark numbers, that's upness, downness, charm, strange, truth, beauty. These values here are partially conserved. What these mean is they're conserved if decay is via strong force, but not conserved if decay is via the weak force. So we can look at my example here. We did not conserve up and down. The total number of quarks was conserved, but the up and downness wasn't conserved. And so this had to have been a weak decay. How do we know the difference? Weak decays are on the order of 10 to the minus 12 to 10 to the minus 16 seconds for them to decay. Whereas if it was a strong decay, it would have been on the order of 10 to the minus 16 to 10 to the minus 23 seconds for the time for decay. So these weak decays, the ones that require a change in the quark flavor, are much slower to occur. So final slide then is looking at these fundamental particles. You should be able to name and know some details about these particles, both the leptons with the 3 generations, the first generation, second generation, and third generation. Each generation is more massive. And the quarks, again, with 3 generations, the first generation, the second generation, and the third generation. All normal matter that we interact with on a regular basis is first generation. Why? Because it's the lowest mass/energy state. But you do have, in existence in life, things that are of the higher generations, the higher mass, higher energy. But the muon is not a stable thing. It will try to decay. It has to maintain the you have to have your lepton numbers conserved, but it will try to decay over time. Here's the examples of baryons, the proton up, up, down, and the neutron up, down, down. And then we have over here the gauge bosons. You should know, I'm not sure why they didn't put the strong in the table over to the left. I guess they just were trying to figure out spacing right. Well, the one on the left, it says united electroweak. Remember from the grand unifying theory, the weak force and the electromagnetic force are combined into one force that's called electroweak. So I guess that's why they put them together instead of putting the strong, the gluons in that as well. Notice the spins are 1 for these gauge bosons. Don't worry about the Higgs boson. That is simply not something we're going to talk about. And make sure you know this information right here, the relative strengths for 2 ups separated by, and we have 2 distances here. Gravitational force is very weak. The weak interaction is also weak, but not as weak as gravitational. Electromagnetic is a little stronger. And of course, these are very similar. And then the strong is, as it says, strong. But the strong force, and the weak force for that matter, are very short-range forces. And so they don't really play a part outside of the nucleus of an atom. All right, that's it for lectures. I hope you've enjoyed this class, and I hope you have a great life.